Compute 4 to the 1th power, 4 squared, 4 cubed, 4 to the 4th power, 4 to the 5th power, 4 to the 6th power, 4 to the 7th power, and 4 to the 8th power. Make a conjecture about the units digit of 4 to the n, where n is a positive integer. Use strong mathematical induction to prove your conjecture. So we'll start with 4 to the 1. 4 to the 1 is just 4, and we need to take note of the units digit, which is a 4 here. And then we can move on to 4 squared, which is 16, but we're going to take note of the units digit, which is a 6. 4 cubed is 64. In this case, the units digit is a 4. 4 to the 4th is 256. We notice there is a 6 in the units digit there. 4 to the 5th is 1024. Notice how it's a 4 in the units digit. 4 to the 6th power is 4096. The units place here is a 6. 4 to the 7th is 16,384. We're just going to emphasize the 4 in the units digit. And then 4 to the 8th is 65,536. Now, if you notice the pattern with the units digit here, we're alternating between a 4 and a 6. Here it's a 4, here the units digit is a 6, and then 4, 6, 4, 6, 4, 6. It looks like the units digit is alternating between 4 and 6. It's 4 if the exponent is odd, and it's a 6 if the exponent is even. So the conjecture here formally will be that the units digit of 4 to the n is 4 when n is odd and 6 when n is even for all integers n greater than or equal to 1. And we're going to use strong mathematical induction to prove this conjecture. Now, the first thing we do with mathematical induction is we identify P of n. In this case, P of n is going to be almost the entire conjecture, except for that universal quantifier at the end there. Now, in the inductive step, we're going to use a very clever trick that will require us to break up the inductive step into multiple cases. A case where k is an arbitrary even integer, and a case where k is an arbitrary odd integer. And because of this breaking up of the cases, we're going to need to prove 2 base cases. That way we'll be able to show that P of 1 implies P of 3, and P of 2 implies P of 4, and then P of 3 will imply P of 5, and P of 4 will imply P of 6, and so forth. So this right here corresponds to the proof of the base case. It will be more clear as to why we need 2 base cases here once we show the inductive step. For the inductive step, we will let k be an arbitrary fixed positive integer with k being greater than or equal to 2. Remember, in strong mathematical induction, k has to be greater than or equal to the largest base case. And then we're going to assume that P of I is true for all 1 less than or equal to I less than or equal to k. Now, we're going to break up this inductive step into 2 different cases. Case 1 is going to be where k is an even integer. Case 2 is going to be where k is an odd integer. Now let's start with case 1, where k is an even integer. Now k satisfies the inequality that would need to be satisfied in order to utilize the inductive hypothesis. If we set I equal to k, then this is how we know that P of k is true. This means that 4 to the k has a 6 in the units place, and that's by the inductive hypothesis. Remember, whenever you use the inductive hypothesis, you need to emphasize to the reader that you use the inductive hypothesis. But we're not trying to prove information about 4 to the k in this inductive step. We're trying to prove that P of k plus 1 is true, which means that 4 to the k plus 1 has a 4 in the units place. That's what we want to show. Well, we know that 4 to the k ends in a 6. So this is going to be some number, some digit, some other digit, and so forth, all the way down to the units digit, which we know is a 6. And we have to imagine what happens if we multiply 4 to the k by 4. So you have to imagine taking this number and multiplying it by 4. Well, how do we normally do multiplication? We start with the units digit. 4 times 6 is 24. And then we carry the 2. But then none of the rest of the number matters here. because once we get the rest of the number, we'll know for certain that the units digit of 4 to the k plus 1 is a 4. So therefore, 4 to the k plus 1 has a 4 in the units place. We know that because once we do this first multiplication, like we normally do multiplication, we get 24, we bring the 4 down, and we carry the 2. But once we bring that 4 down, that units place is a 4, and it's locked in. So that means P of k plus 1 is true. So now we need to move on to case 2, where k is an odd integer. Now, in this case, k still satisfies this important inequality that needs to be satisfied in order to utilize the inductive hypothesis. But since k is an odd integer, then the inductive hypothesis says something a little bit different this time. This says that 4 to the k has a 4 in the units place. Now that means we can write 4 to the k as some number with a bunch of digits, but then the last digit is a 4 this time. And we need to multiply 4 to the k by 4 to get 4 to the k plus 1. And that would require us to multiply this number by 4. Now, the way we normally multiply numbers is we start with the units digit here. 4 times 4 is 16. So we'll write a 6 here and we'll carry the 1. And now we're going to get the other digits, but the other digits don't really matter because once we have this units digit locked in, we know what the units digit is going to be. 4 to the k plus 1 has a 6 in the units place. And this means that P of k plus 1 is true. Now, why is it that we get different conclusions for each case, but in both cases, P of k plus 1 is true? Well, that's because in the first case, k plus 1 is odd since k is even. If k is even, then the next consecutive integer would be odd. And the conjecture says here about odd integers that the units digit of 4 to the n is 4 when n is odd. And so we're trying to prove that 4 to the k plus 1 has a 4 in the units place, which is what we did here. But in case 2, k is an odd integer, which means that k plus 1 is an even integer. And the conjecture says at the top here that when n is even, the units digit is a 6. And that's what we showed, that 4 to the k plus 1 has a 6 in the units place, which means P of k plus 1 is true. In either case, P of k plus 1 is true. And so therefore, P of n is true for every positive integer by strong mathematical induction. Thanks everyone, and I'll see you in the next video.